All right. Well, we are going to talk about today is we're going to go on to 2.4, which is talking about continuity and one-sided limits. So without further ado, you can see what we're going to hopefully be able to do here. Solving one-sided limits, hopefully be able to define continuity and discontinuity, which we already have in a little bit, and then identify the intervals where a function is continuous by identifying where the function is discontinuous, label discontinuity, and in a further video, we'll talk about intermediate value theorem. So without further ado, here we go. Well, a little warm-up. We're going to find the limit, if it exists, with this limit right here. Now, what you need to know is that when we find limits, one-sided limits, this is a one-sided limit. We are finding with this one, when you see the minus sign, this means this is a left-sided limit, which we've found before. Now, left-sided limits, just like right-sided limits, equal the limit as x approaches 4 by itself. And if it equals x is 4, the right and left side limit will be the same. So when we see a function like this, what we have to know is the limit as x approaches 4, does that exist? So if the limit as x approaches 4 for this function, the square root of x minus 2, all right, x minus 4, if that right there, if this exists, okay, if this exists, all right, then we know that the limit as x approaches 4 from the right of this function, we'll just call that f of x just so I don't have to get right every time. All right, f of x, that's going to equal the limit as x approaches 4 to the left of f of x. All right, so right here, I'll just say this one is, all right, it will exist. All right, we could graph it, but it does have two sides. And so what we would do is we would solve it just like any other limit. We would use first off direct substitution. All right, so we plug the 4 in there. And we have the square root of 4 minus 2 over 4 minus 4. And we have 0 over 0. Once again, 0 over 0 is indeterminate form. This talks about removal of continuity, which we'll talk about a little bit more today. Okay. And we know that we can solve this now by using the conjugates. Okay, so the conjugates. So we're going to simplify this. The square root of x minus 2. All right. X minus 4. We're going to rationalize this technique. All right, let me take the limit. Just 4. Left. All right, we're going to multiply by the conjugate. The conjugate rationalizing the square root of x, and we're going to go plus 2 over the square root of x plus 2, and we're going to distribute this through into our algebra. All right, so here we go. When we do this, we're going to take the square root of x times square root of x, which is x. Middle terms for the conjugates cancel out. So we have minus 4. Hey, what do you know? X minus 4. Woo! All right, right there. We have the square root of x plus 2. We're going to eliminate this whole by canceling out these two values. And now we take the limit as x approaches 4 to the left, which means we just plug it in again. You have 1 over, all right, the square root of 4 plus 2, which actually equals 1/4, because that's 2 plus 2 is 4. And that's our limit. Awesome, huh? Now, that's cool. So solving limits with one side is the same way as solving limits with both sides, as long as we know that the limit here exists and these two are going to be equal. So that's pretty much what you get for most of the limits. However, you come to some limits where you have a function like this, the square root of x, where you have a strange function. Because originally we'd think, okay, we would plug this in here, direct substitution, all right, and we would get the square root of 0, which equals 0. All right, so that means the limit as x approaches 0 to the right, and remember this is to the right, all right, to the right, well, that would equal the same thing. That would also get the square root of 0, which would be 0. Now, this is correct, okay, this is correct. However, this one actually does not exist. How do we know that? Well, essentially, if we were to do a table, all right, and it's kind of easier if you just know what the square root of x looks like. If I were to graph that square root of x, the square root of x is actually a function that looks like so. Okay, if you actually plugged in values into this function, all right, and we said this was f equals the square root of x, so I'll put in f right here, all right. And so if we plugged in values, we realize that as we get closer to 0, to the right side, yes, to the right side, we can plug in 0 like 0.0001 because you're approaching this value, all right. So as I approach in, my c value gets closer to 0. I see that my y values up here, the intended height is going to equal 0 as well. So that makes sense. This is true. All right, so this one's okay. Okay. All right. However, This limit, as you approach from this is a two-sided limit. That means the limit to the right and the left has to be equal. Well, right here, we see this is going to equal 0. However, if I try plugging in a value like negative 0.0001, well, what do we know? Can we plug in a negative, all right, into a square root? The answer is no can do. No, that's imaginary, all right? That's an imaginary right there, and that'd be the square root of 0.0001, all right? And that don't work out, all right? Yeah, so this one actually doesn't exist. There is no value, all right, to the left, all right, right here, to the left of the square root of x. So this one actually is not equal to 0. All right, this limit, because it only has one side right here, this one does not exist. Why? Because, all right, the limit as x approaches 0 to the left of the square root of x, that one does not exist. And for a limit like this to be true, remember the right and the left side have to be equal. And that's what we got there. All right. Now, also when you have this, all right, you see a lot of limits when we talk about one-sided limits, or you deal with piecewise graphs. So right here, if we have a piecewise function, all right, essentially we need to figure out if the limit as x approaches 2 for f of x. All right, once again, if it's piecewise, this is weird because usually we look at what are potential breaks. And how do you know where there's a potential break with piecewise graphs? You look at the values that just underlined, okay? Look at these values because this right here, if you look at the function itself, all right, this, my friends, is a line. So if I were to graph this, kind of just think about the graph, okay, real quick. All right, this right here, I'm graphing a line, and I'm starting with all x values at 2 and less. So if I plugged in 2 into here, I would get 1, 2. All right, that'd be 2. All right, so I plot that point right there. Every value less than that, so I plug in 0, that'd be 1. All right, like that. And so essentially, what I have a graph looks like that. I'll change color. All right, right here, and we have this graph right there. We then plug in a value that's greater than 2, so I plug in 2 in there again. Well, here, as I plug in 2, all right, this is the open circle because it's not equal to. So if I plug in 2, I'm going to plug it into there. So I plug 2 into there. And starting at 2, I get 1. So I'm going to open circle here. And then I plug in any other value, so I'll plug in 3. Any value is greater than that, so I'll plug in 3 right there. I have 0 right there. I graph that. Now, this is the thing. Notice how we have 2 different values. So we can see graphically, as we approach 2, the limit as x approaches 2 to the right of this function f of x, well, where do we plug that into? That's to the right of that. That means all x values greater than 2. So we're actually going to plug, in order to figure this limit, we're going to take 3 minus 2. I'm plugging into this function right here, and that's going to equal 1. All right? And I can see that, yeah, that's going to equal 1. Now, if I take the limit as x approaches 2 to the left of the same function, I realize I have to plug in this 2 to the left, which is all x values less than that. So I have to plug this 2 into this function. So I have 1/2 times 2 plus 1. And what we have right there is going to equal 2. Well, these 2 values do not approach the same value. So guess what? We would say this limit right here does not exist. All right. This is actually jump discontinuity. All right. The limit from the right and the left do not equal. And therefore, that limit doesn't exist. All right. Now, right here, I have a different function. And we're looking for what is the value as x approaches 5. Well, if it's pushing 5 to the right, all right, 5 to the right, that means I'm actually plugging in values which are going to be greater than, all right, greater than 5, greater than 5. So which values are greater? Well, that's that function right there. So to find this limit, I'm going to use direct substitution, just like I did with these right here. But I'm going to plug this 5 into this function right there. So I go 10 minus 3, all right, e to the 5 minus 5, all right? And what we have then, it's going to equal 10 minus 3, e to the 0, which we know is going to be 1. So we have 10 minus 3, which equals 7. Our limit equals 7. Okay? And actually, if we want to figure out, does the limit, and this is the extension, so I'm just going to extend this problem a little bit. All right? If I want to extend this problem a little bit, and I know this limit is 7. Now, if I want to figure out, does the limit as x approaches 5 for g of x, Well, to figure out this exists, guess what? I already know the right is 7. Well, I want to know what happens when the limit as x approaches 5 to the left of g of x. Well, what do? I take 5, and let's plug in the bottom function, because when I want to figure out the left, all right, the left side, all right, really thinking about all x values less than 5 in this case, right? So that's the left. So I've plugged in 5 into here, so I have 10 minus 3/5 times 5. Cancel. 10 minus 3 is, oh, what do you know? In this case, both these limits are equal. Therefore, we would say that the limit as x approaches 5 is also equals 7, all right, because they approach the same value, all right? Unlike this one over here, and that's what we got. So limits to the right and left are existent, but the limit at 2 without any sign, that's what we refer to as a two-sided limit, okay, two-sided limit. All right, so that is how we solve one-sided limits. So you see a lot of them, all right? I'll have to go back right here. I see a lot of them when you talk about piecewise graphs. When you talk about 2, this is a two-sided limit again. Two sides have to agree in order to work out, all right? One-sided limits, you're looking for, all right, everything greater than this value, okay, coming from the right side, and this is coming from the left side, all right, and that's how we can solve that. So piecewise, all right, make sure you pick which function you're going to plug into to figure out the value. All right, well, I'm going to stop it here and give you another video, make these a little bit shorter. So this is for one-sided limits, all right, so hopefully this helps you out, and I'll continue with continuity in the next video.